Hello, welcome to the channel, and in this video I'm gonna quickly demonstrate how we can fine-tune any model to output our desired result. So basically the idea here is that you have a model but you need it to do a very specific task. So for example, we may have a task like transforming a set of instructions and an input into a very specific structured output. So for example here, in this case, we have an input which is convert the following book description to JSON, and then we have a description of a given book, and this is a small training dataset. And then our goal here is to transform it into a very specific JSON format with a title, an author, a publication year, the related genres, and the themes, etc. So here we have a very specific JSON format, and we may need this format for some sort of an API or something else, but the core idea is that we need a very specific output. Now, one way to do this would be prompt engineering, aka alongside with this instruction, we could provide this JSON format. But this is not always very efficient because models tend to hallucinate, so in some cases it may add additional fields to the JSON, and also this makes the input much larger. Now, to solve these problems and to ensure that the model outputs whatever we need it to output, we can circumvent this by fine-tuning our model. On top of that, this will make the model faster since the input is inherently smaller. So basically, let's see how we can go about this. Now, first and foremost, you can go into Open LLM leaderboards on Hugging Face, and here you can see a ranking of all models by certain criteria, and you can choose your criteria based on your task, and then you can sort these models. I'm gonna be using the Falcon 3 7 billion instruct because it suits my needs and it is pretty fast. And having chosen my model, all I need to do is copy the name of this model, because we're gonna be working directly with Hugging Face. Now, on top of that, you will need a Hugging Face account. So I've made a new one here, and then you will want to go into access tokens, and you will want to confirm your identity. And once you have done so, you will be able to see your tokens, and all you need to do is create a new one, then give it a name, and you want to give it repository permissions, and if you have an organization, you can find it here and also give it permissions to manage the repositories of that organization if your repository belongs to the organization and not to your personal account. So basically, once you have given it the necessary permissions, you can create the token and then copy the token, and then you'll be able to use that token to authenticate with Hugging Face and directly upload your models on here. So now from here you want to go into your profile, and depending on whether you're using a private profile or whether you're using an organization, you will need to switch between the two. In my case, I'm going to go into my organization here, and you can click on new and then model, and then you can create a new private model which you're going to be using. And all you need to do again is to copy the name of your repository and your model name. So basically you will need this string right here, so you can just press copy up here once you have created your repository. With your repository initialized, you can let's actually take a look at this existing repository first. So basically if I go into files and versions, you will be able to see a low rank adaptation of my model. So we're using LoRA, and we're going to be discussing LoRA in just a moment, but essentially instead of retraining the entire model, which would take ages and be quite inefficient, we're training certain trainable parameters and storing them in our Hugging Face repository. So essentially here you can see the adapter model.savetensors file. This file essentially contains the LoRA parameters, aka small a and b matrices injected into our attention layers in a single file, and it's a pretty small file at that. And then we have a few other configuration files which are used to inject our parameters and manage the way our LoRA is applied. So essentially, this is the entirety of our fine-tuned model, and it's quite small, and it is very efficient to use Hugging Face to store your models like that. So basically, with that said, your repository will be empty, and all of your your low rank adaptation will be automatically uploaded into your repository every time you fine-tune and train your model. So having that said, let's go back, and actually I think it's high time we open up our code. So again, in here we have a dataset. So we have a file called data.jsonl, and in here I have created a set of objects. So basically I have quite a few objects, and as you can see, I separate them by lines, so I don't have commas in between each object. And then the format I've chosen is to have an instruction here, an input, and then that is followed by my output. So having that said, we want to use this sample set to fine-tune our model to output this specific output right here. So we're very interested to make sure that this JSON structure is adhered to. So having that said, for actual training, you will probably need much more data, and depending on your task, you will either need to collect or craft the data yourself, or maybe use an AI to do it for you. So now let's go into our actual script, and this script will be performing our fine-tuning. So this is a simple Python script. I'm gonna be using Anaconda and a pre-made environment with the dependencies installed to run said script, but you can do it in whichever way you want to. The major requirement here is to have CUDA installed on your system, and there are plenty of tutorials on how to do it. So having that said, let's go ahead and let's review each separate section. So to begin with, we have a helper script called show training data samples, which simply outputs an n number of your training data samples to verify that your training data has properly loaded. So next up, we have two methods to generate our outputs here. So the first one is generating text from a pre-trained model. So basically we're using our base model without fine-tuning, and essentially we just want to test it and see what the output is. So in this case, all we're doing is saying pretrained model.eval to set it in to work in evaluation mode. Then we're initializing our inputs here by using a tokenizer and our prompt. And then we're ensuring that we're working with the first CUDA device available. Then we're generating an actual output and decoding it into human readable text. And this is how we are generating our output. So next up, we have this function here, which is used to generate an output from our pre-trained model. So this is the model before we fine-tune it, and we want to see what the output is. To do that, we're setting the model in evaluation mode. We're initializing our inputs using a provided tokenizer and a prompt. We're offloading that to the first CUDA device available. Then we're generating an output, and then essentially we're decoding the output into human readable text, and this way we want to see what the output of the base model is, to then see if we've made any improvements to it. Now the second function is pretty much the same, so basically this is a little bit redundant, but we're creating a second function to have a distinction between the two, but in essence these two functions are doing the same thing. But instead, in the second function, we will be providing the fine-tuned model here, but the general functionality is the exact same. Then we have our main training script, and here we want to essentially process our example data. So basically, all we're doing is we're returning a string which will concatenate our objects here into an actual string readable by our model. So instead of feeding it an object, we're feeding it a string, and all we're doing is basically breaking down the examples object here into parts and concatenating them into a string like this. Next up, we have our tokenizer function, That is quite self-explanatory, and I'm not gonna go into details when it comes to these generic AI functions. And then we have our actual fine-tuning process. So first of all, we're checking if CUDA is available, and in many cases you will have problems when you're setting up Anaconda environments if you didn't set up the environment correctly, where CUDA will be unavailable. So make sure you have installed CUDA on your chosen environment and that your distribution of torch, etc. supports CUDA. Having that said, we're then providing our Hugging Face token from before. I'm gonna be removing this token once we're done with this video, so don't worry. And we're calling the login function from Hugging Face to essentially authenticate within this session and be able to interact with our repositories. Next up, we need the name of the original model. So this is the original repository and model. So now down here you have your standard bits and bytes configuration here. So this is used for quantization of the model. Next up, we're setting up the tokenizer here. Then we're setting up the base model and we're providing the model name and the previous bits and bytes configuration. And then we have a test prompt here, which is just a prompt in a similar format to what we've defined in the preprocess function. And this is important that your prompt follows this format because the model will be trained on this format. So in essence, what we're saying is that we're given an instruction here, we're given an input, which is essentially a description of a book, and then we are awaiting a specific response. Next up, we have our output from our pre-trained model. So this is where we're using the function from before to simply output what the original model would have generated to see what the output is. So next up we have our data path here. So this is the path to our JSON-L file. Then we have a seed here. You can set a seed to ensure that you can reproduce your certain results, such as, for example, consistent data splits and training outcomes, but this is quite optional. Then we are using load dataset here, which loads the dataset from the JSON file, and we're saying split equals to train to split the dataset into a training partition for further processing and training. And down here, we're essentially then taking our dataset and basically we're applying our preprocessing function to every example in the dataset. And then down here we're using filter, and this will filter out any data entries where the text is missing or none. This is optional since we know that this won't happen with our training dataset, but for an auto-generated or very large training dataset where you have uncertainty, this is a good step to have. Next up we have our show training data samples function, which is applied to our dataset. This simply outputs a piece of the training data to ensure that the dataset is correct and that our data is valid, and you can set this number to more than 1 if you want to output more than 1 examples. So this is pretty straightforward. And then we have our tokenized dataset, and basically it tokenizes the text inside of the dataset using the tokenizer, and it processes the dataset in batches for efficiency. It removes the text field after tokenization since it's no longer needed, so we are saying here remove columns, and we're specifying the text column. And I should mention that up here what we're doing is that we're essentially, as I said before, we're processing our input and we're bringing it into this format where we only have a text column, and then we're removing the previous columns, which are these 3 columns. But then after we've successfully mapped our dataset, we want to remove the text column as well because we don't need it anymore. And we're setting this to a single process operation, and then we want to split our dataset, and we want to make sure that 10% will be used for validation and 90% will be used for training. So here we're extracting our training dataset, and here we're extracting our evaluation dataset. So next up, we are preparing the model for training. So this essentially prepares the model for low bit precision fine-tuning, and it ensures that the model will be compatible with quantized training, and it does that by freezing certain parameters and well, applying certain optimizations, but we won't go into that too much. Then we're saying model config.useCache equals to false. This may be a necessary step in many cases. In essence, it disables caching during training, because it may cause issues when it comes to parameter efficient fine-tuning, such as is the case with LoRA. So if you were to not disable caching, this would have caused issues with the actual fine-tuning. So in this case, we do not want caching for this model, so we're disabling it. And then we have our parameter efficient fine-tuning configuration. And parameter efficient fine-tuning is essentially an umbrella term for ways to fine-tune your model. So as you can see here, we're importing LoRA, a LoRA configuration from parameter efficient fine-tuning. And what LoRA does is essentially it adds a set of trainable parameters to the original model. So essentially, instead of adding new trainable layers to the model, like is the case with adaptive layers and other types of parameter efficient fine-tuning, or instead of modifying the original prompt, which is another technique sometimes used in parameter efficient fine-tuning, what LoRA does, it introduces additional parameters, so it freezes the original model, so the original model is untouched, and then it adds additional parameters which are then applied to that model to modify the output of that model. So instead of modifying the model or introducing new layers to the model, you're simply adding additional parameters or matrices to that model, and then you're modifying these parameters, and what we're actually saving in our Hugging Face repository are these additional parameters. And this is why our Hugging Face repository, the contents of it is so small. It is because we're not storing a modified version of the original model, we're storing the trained additional parameters. So having that said, this is what our LoRA configuration does here, and we're not gonna go into depth when it comes to configuring the LoRA config, but there is plenty information online on this type of configuration, and it will depend on what you're actually trying to achieve. So we're not gonna go into depth when it comes to the actual configuration parameters here. Now, next up, we have this line here, a get parameter efficient fine-tuning model. And basically, it simply applies the LoRA configuration to the base model, and it essentially adds the trainable LoRA layers. And then we have print trainable parameters, and this will print the number of trainable parameters in the model, and it will basically highlight how LoRA reduces the number of trainable parameters compared to full fine-tuning. So essentially, you'll be able to see how drastically lower the number of trainable parameters is in comparison to fine-tuning the entire model. And this is one of the major reasons why people use LoRA, is because it is fast, it is efficient, and it doesn't take much space. So having that said, then we have the training arguments here. So these are our core training arguments. And again, I'm not gonna go into depth here, but I do want to mention this last part, which is push to hub. This will automatically push your LoRA into your repository, and here I have specified a strategy which is called every save. So every time we have modifications to our model, it will be pushed automatically to our repository. And here we're providing our token, which we've defined up here, and this will take care of pushing our model. And that's pretty much it. Then we have our data collector, and the data collector handles padding and batching of input data during training, but we won't go too much into it right now. Then we have our trainer. It initializes the Hugging Face trainer object, and then we're basically providing certain arguments here as well, and this will perform the training loop. So in this case, we're providing the actual model, we're providing the training arguments, the training dataset, the evaluation dataset, and the data collector, and this will handle training for us. And then we're starting our training, and we're saying trainer.train. This will automatically fine-tune the model based on the dataset, and then it will save the changes to our Hugging Face repository. And once we're done, all we need to do is we need to say generate text from fine-tune. So we're using our previously defined function. We're providing the model here, we're providing the tokenizer, and we're providing our test prompt from up here. And this should produce different results from our original test up here, which would signify that the training has gone correctly. And yeah, that's about it. That is how you train and fine-tune your model. So now let's go ahead and let's actually run our script here. And for that, I will open up my Anaconda. So from here, I'm running my Python script, and this will begin the fine-tuning process. It will first load the original model. It will also check to see if a CUDA device is available, which it is. So basically, this is my current graphics card. And this has started loading the original base model. So as you can see here, we are testing our pre-trained model with our input, and this is the original output. So as you can see, we do get a JSON, but the problem is that we have a bunch of fields that we do not need, and the model is essentially guessing at what it should do. Now, if we had specified the JSON format, it would probably be able to follow it, but that would have increased the original input, because we would need to have an example for it. And in some cases, this makes training, especially if you're running the model continuously, much slower. And as you can see, here is our concatenated text. And then down here, we have the number of trainable parameters, which is 1,000,000, while we originally had about 7 billion total parameters. So this makes a very small portion of the actual parameters trainable, which is incredibly good when it comes to training efficiency. As you can see here, the training is ongoing. We can see the loss, we can see the learning rate, etc. And as you can see here, we can see the training progress. So let's wait for this to finish, and let's see what the model outputs. And now, as you can see, we're done. Well, given that our training dataset is quite small, it's no surprise that we're actually done in such a short time. And as you can see, we're testing our fine-tuned model with the same input, and now the output contains a title, an author, a publication year, the genres, the themes, and the setting, which is exactly the response we're waiting for. So this has worked perfectly, but I have to warn you that we were working with a very small data set, And this is a very simple task for this model, and with some prompt engineering, if you didn't mind the space, you could achieve pretty much the same thing. But again, fine-tuning a model serves mainly the purpose of making your initial prompt smaller and making the output more precise. So in this case, this has worked great, but in your case, you will need a much larger dataset to ensure that your loss is as low as possible and that your output is as precise as possible. On a side note, I realized that I did not explain how you would use your trained model from your repository to generate responses. So a standalone function, which is outside of this process, would look like this. So you have this function here, which requires a Hugging Face repository ID, your base model, a tokenizer, a prompt, and a max new tokens argument. So most of this down here is identical to what we saw before. So we are creating our base model by using a BME config here. But the difference is that here, to import the existing model from our repository, we need to use PEFT model, which we're importing from PEFT up here. And basically, what we're doing is we're saying that we want to use a pre-trained model. So we're providing the base model here, and then we're providing our Hugging Face repository ID. Again, we're setting our model to evaluation mode. We're preparing our inputs, and then we're generating and decoding our output. So this is a standalone function to use after you're done training and fine-tuning your model. Now, if you have any questions or suggestions, you can leave them in the comments below. Hopefully this video was helpful, and if you want to support the channel, make sure to like, share and subscribe, and I will see you in the next video.